Hello and welcome to this 7th lecture in this series on atomic and molecular structure and spectroscopy. At the end of the last lecture we touched on vibronic transitions, and this is where we have vibrational fine structure superimposed on an electronic transition. So we observe the vibrational transitions which take place between the electronic states. Of course, this is associated with a selection rule. And this selection rule we saw last year as part of the second year spectroscopy module, and effectively delta V, so the change in the vibrational quantum number is unrestricted. Delta V can take any value. What we're going to do now is go and have a look at Rovibronic transitions, and this is when we have vibrational and rotational fine structure superimposed on an electronic transition. So we can think of now, there's three things happening as a transition takes place. We're going from the ground electronic state to an excited electronic state, but we're also going from a ground, we're going from a ground vibrational energy level up to a different vibrational level in our electronic excited state. And at the same time, we've got the possibility of changing rotational energy level between our initial state and our final state. Of course, again, we've got selection rules. So first of all, for sigma-sigma transitions, so of course sigma we've seen we only see for diatomic molecules. In this case we have delta J, so the change in the rotational quantum number can only be plus or minus 1. This comes about for the requirement that angular momentum is conserved, and if you have a sigma to sigma transition, then there's no change in the angular momentum of the electronic state, but the incoming photon, which excites the system, has 1 unit of angular momentum. So this has to go somewhere, and this goes into the rotational energy. If for all other transitions, this restriction is slightly different, so we have delta J equals either 0 or plus or minus 1. This leads to a whole series of branches in our spectrum, and hopefully you remember most of this from the second year course. Hopefully you remember this equation here, which looks at the population of rotational energy levels with quantum number J with respect to the lowest rotational quantum number. And as the gap between rotational energy levels is fairly small, typically between 0 and 10 wave numbers, it means that at a normal finite temperature, say room temperature, a lot of the rotational energy levels will be occupied. So it means we'll see transitions from a lot of rotational levels, and this leads to the branches in the spectrum. Again, we saw this last year. So it's the population of these rotational energy levels which gives rise to the shapes of these branches. Last year we'll have seen the P branch and the R branch. So P branch where delta J equals minus 1 and the R branch where delta J is plus 1. But we've just seen now that if we have a Rovibronic transition, that delta J can also be equal to 0, and this gives rise to a Q branch. Let's have a look in detail at some of these branches. If we just have a Rovibrational spectrum, so Rovibrational fine structure, we'll have our J double primed. We'll have some rotational levels here. You'll remember from last year that as you go up the rotational quantum numbers, we go from 0, 1, 2, 3, the energy levels get further apart. And if in this case, if we have, let's concentrate on drawing this first. There we go, that's okay. So here we have J prime equals 0, 1, 2, or 3. So for this case, if we have the equilibrium bond length in the ground state is more or less equal to the equilibrium bond length in the excited state, as a consequence this means that B, the rotational constant in the ground state, is going to be approximately equal to B primed, so the rotational constant in the excited state. Then we can observe a number of transitions. You'll remember the J branch has delta J is minus 1, sorry, the P branch and the Q branch has delta J equals +1. So let's draw some transitions on. So the first transition in the P branch is going to go from J double primed equals 1 up to J primed equals 0. Second transition is going to go from J double primed equals 2 up to J primed equals 1. And the last one, at least on this diagram, will go from J double primed equals 3 up to J primed equals 2. We can label these states, so it's the P branch, and we label them according to the lowest, the quantum number in the initial state. So this is going to be P1, then it's going to have P2, and this last transition is P3. Now let's have a look at the sorry, it's not the Q branch. This is the R branch, getting ahead of myself. So in the R branch we have delta J equals +1, so the first transition is going to go from J double primed equals 0 up to J primed equals 1. Next one's going to go from J double primed equals 1 up to J primed equals 2. Next one is going to go from J double primed equals 2 up to J primed equals 3. And we can label these in the same way, so this is R0, R1 and R2. So this is R0 because it starts in J double primed equals 0. If we now think of an electronic transition where we have row vibrational fine structure, let's have the ground state. So our state's getting further apart, so this is again J double primed equals 0, 1, 2 and 3. And if we now say that the equilibrium bond length in the ground electronic state is shorter than the equilibrium bond length in the excited state, this has the consequence that the rotational constant in the ground electronic state is going to be larger than the rotational constant in the excited state, because we know there's a reciprocal relationship between, or an inverse relationship between the bond length and the rotational constant. So this means in the excited state, these states are actually going to be closer together. Let's try and draw it. Okay, so here we have J primed equals 0, 1, 2, 3. And then we can draw the transitions on as before. So I've already drawn P and R branches on, so I'm not going to draw those on this diagram. But I will draw the Q branch because the Q branch is now allowed. So the first transition in the Q branch goes from J double primed equals 0 up to J primed equals 1. Then we get the transition 1 to 1. We get the transition 2 to 2. We get the transition 3 to 3. And we can, so this is the Q branch, so we have delta J equals 0. And again we can label them in exactly the same way, so this one here becomes Q0, then we have, next one is Q1, then Q2, and this last one here is Q3, because we've started in J double primed equals 3. Okay, so that's in principle the transitions we're looking at. How do they look like in a spectrum? So this spectrum you'll be familiar with from last year. So this is simply a row vibrational spectrum of a diatomic molecule, so something like HCl, where B primed is similar to B double primed, so we get P and R branches as we would expect. If you now look at an electronic transition, so we're looking at this transition between the C state and the A state. If we do it at low resolution, we get this sort of structure here. We can see straight away there are 3 features in this spectrum. So one on the left, this big one in the middle, and then sort of one on the right. If you look more closely at this spectrum, this is the structure that it has. So we'll have the P branch to low energy, we have the R branch to high energy, and the Q branch in the middle. And we'll find the general features that we'll have seen previously. So here in the P branch the lines get closer together, the peaks get closer together. Here in the R branch they get further apart, and we can see that in the Q branch the actual transitions themselves are very close together. So that gives us an idea of what an electronic spectrum might look like if we see the row vibrational fine structure. Okay, let's have a look at some of the equations in order to be able to calculate some numerical properties for these spectra. So we're looking at the rotational fine structure within a spectrum. You should remember from last year that f of j, so this is the rotational term and has units of wave numbers, is equal to b j plus 1. So where b is the rotational constant and j is the rotational quantum number. Now if we've got a peak in the R branch of a row vibrational spectrum, we can write an expression for this wave number. So nu tilde of R of j, and this was going to equal to the purely vibrational part, so let's call that nu tilde 0, and then we're going to add the rotational part, and if it's in the R branch it's going to be going from a state j up to a state j plus 1. So the upper state, let's call it f primed of j plus 1, and we're going to subtract the energy of the lower state, so we can call it f double primed of j. So now we can substitute in for f primed and f double primed of j, so the two rotational terms. So we get nu 0 plus, so this is going to equal b primed, because we're in the the final excited state, j plus 1, j plus 2, minus b double primed, j plus 1. So you see here, all I've done is inserted this expression here for f of j into this expression here. So for this term here, when we start at j plus 1, it means j plus 1 here is now j plus 2, and then we've got j plus 1 in the second term. Okay, let's simplify a little bit. This is what I'm going to do is jump a couple of steps here, but this is something for you to check that you can do. So we get nu tilde. What I'm going to do is actually group things together according to their powers of j squared. So this gives us b primed minus b double primed j squared plus 3b primed minus b double primed of j plus 2b primed. Okay, so this was just by multiplying out these parentheses and then grouping terms together. And now once we have this expression, we can actually do some useful things with that, and we'll come back to that in a minute. Some homework for you now. In exactly the same way, you can show that the wave number of peaks in the P branch can be written in using this expression here, so that'll leave that for you to do in your own time. You might want to stop the video and do this now. Okay, so one of the consequences of having different bond lengths in the ground state and the excited state is that interesting things can happen with our line structure within the spectrum. In particular, we can get such a thing called band head formation. This is an example here, so you can see in the P branch it just looks like normal, so we've got the lines going out. But in the R branch we can see there's something funny happening here. If you have a closer look, we can see what happens is the J values were gradually going up, so the peaks go this way and get closer together, but then they start coming back on themselves, so they go sort of round like that. So this happens when you have a bond length which is very different in the ground state to the excited electronic state. Let's have a look at this in a little bit more detail. Here's actually, before we do that, here's actually the transition for oxygen. So we're going from the ground triplet sigma G minus state, so denoted X, up to an electronically excited state, so the B state, triplet sigma U minus. And here we have the P branch and the R branch. Obviously we don't have a Q branch here because for a sigma to sigma transition you can't have delta J equals 0, so there's no Q branch. But you can see the P branch is as normal, but already straight away here the R branch comes out and sort of curls around that way. So this is quite a common phenomenon. And whether we get, and this thing here, this point here at the end, is called a band head. So this is where the peaks start to turn round on themselves. And you can get band heads forming either in the R branch or in the P branch, and this tells us useful information straight away about the different bond lengths, the difference in bond lengths between our two electronic states. Okay, so we've seen that bandhead formation can occur. Let's have a look at some of the maths to work out for which value of J this bandhead will form. So if we have bandhead formation, so for bandhead formation in the R branch, and this will happen if B primed, so the rotational constant in the excited state is less than B double primed, which also means that the equilibrium bond length in the excited state is larger than the equilibrium bond length in the initial state. So if we have a band head, this means that the wave number of J is going to reach a maximum. It's going to increase, become a maximum, and then the wave number is going to turn around again. And we can write this mathematically. So dr of J dJ is 0. So this is true at a maximum. So if you have a look at the expression for R of J, so the wave number of a peak in the R branch, this is the expression we had just before. If I now just take the rotational part, I'll leave the vibrational part out because that's just a constant. We have B primed minus B double primed times J squared plus 3 B primed minus B double primed of J plus 2 B primed. Okay, so now we can work out dr of J dJ. So here we get 2 B primed minus B double primed of J plus 3B primed minus B double primed. Okay, and that we know is equal to 0. So to now find the value of J for which this occurs, we can just rearrange this equation and make J the subject. So J for this maximum in the band position is going to equal 3B primed minus B double primed divided by 2 B double primed minus B primed. Okay, I've just gone directly to the answer there, so you should check that you can work this out yourself. Some homework for you now. So we've done it for the R branch. Now you can go and do it for the P branch, and the expression you get is this one here. So you should be able to now derive this expression. Okay, that more or less brings me to the end of this course. So in this lecture course we've looked at various aspects of valence theory and atomic structure, electronic spectroscopy and so on. This includes thinking about the Lewis octet approach, see where this falls down. We've looked at atomic structure and term symbols. We've looked at linear combination of atomic orbitals, and this gives us insight into molecular electronic structure and the term symbols. Once we've got various energy states, we can look at selection rules for transitions between them, and then in this last lecture and the previous lecture we've looked at some of the implications for electronic spectroscopy, so things like the shape of the spectrum, whether we have a continuum or not, and then today whether we get a bandhead formation or not. So that brings me to the end of this course. You should now complete the final Blackboard quiz associated with this lecture, and I'll see you in the timetabled session. That brings me to the end of this lecture.